Hello and welcome to our presentation. I'm Lauren and I worked with Sam on our project on vibration control with CMGs. The research paper we went through is on mitigating the vibration of a flexible spacecraft. This would help with sensitive instruments like cameras from having to experience excessive vibration if natural frequencies are hit. The control moment gyros are dual gimbal and variable speed, meaning that there are 3 degrees of variable motion on each of the 4 CMGs. The model controls both pointing and vibration suppression. The vibration considerations are modeled dynamically through different frequency modes and mode shapes. Some of the model assumptions are small deformation in the elastic region. The center of mass is in the same position for the wheels and the gimbals. The gimbal frame acceleration is negligible, and the wheel speed is significantly greater than the gimbal angular rate. In this problem space, we will be analyzing one flexible component on a spacecraft that is subject to vibration at natural frequencies.
The dynamics of the plate coupled with the CMGs can be represented with the equation below, and this pretty much represents the movement of an element of mass translationally and rotationally within the plate. AJ is the mass moment of inertia of the entire system, so that includes the inertia of each outer and inner gimbal and rotor for each CMG. Omega dot J is the change in angular velocity of the plate. HAJ is the angular momentum coefficient of the entire system. Tau double dot J is the acceleration of the assumed modal vectors. XJ omega is the non-linear torques that are a result of the couplings of the angular velocity, elastic velocity, and angular elastic velocity. DGV is the torque due to the momentum exchange between each CMG and the plate. And TJO and TJQ are the active command torques. H, X, and T, as well as J, are not constant, as vibration will cause each CMG to displace relative to the center of mass of the plate, and the rotation of each gimbal frame for each CMG will continually move the inertial components of each inner and outer gimbal. The change in attitude is the same as the change in attitude we use in our class.
Control laws are the other section of the simulation where we take inputs from the propagated dynamics and solve for new updates in the control moment in the controller law and how each CMG is going to achieve that maneuver in the steering law. In the controller law, Kp and Kd are gains based on the state and angular velocity of the body. J sub j is the inertia matrix of the body to account for how a moment will be affecting the body. And the last term accounts for the motion at each CMG due to the vibration. In the steering law, Q and N are gains. The capital B matrices represent the current states of each CMG. The V matrices are part of the B matrix singular value decomposition. Lambda and E contribute to the mode frequencies, and the lowercase b matrices represent the CMG states as well as the vibration displacements. Theta dot G will solve for the gimbal rates, and theta dot W will solve for the wheel accelerations. Here's an overview of the Lyapunov stability proof to show that the control law presented in the research paper is indeed stable because L dot is shown to be less than or equal to 0. However, this does not prove asymptotic stability, so the rest of the proof must be proved with LaSalle. LaSalle's theorem shows asymptotic stability with the invariant set shown here as pi. And now we'll go into a quick demo.
So the paper uses a finite element modeling system to come up with the mode shapes for the first 6 modes. And then with each mode shape for the plate, they derive the displacements for each like nodal like element mass on the plate. Since finite element modeling is going to be out of scope of this class, we have decided to model the displacements as 0. So essentially, the simulation is a plate starting at a certain attitude, moving towards its commanded attitude, and then staying and maintaining that pointing at that commanded attitude. And now we'll just go into the dynamics block. So the dynamics block takes in the gimbal rates and the rotor acceleration that the steering law will calculate, as well as the initial conditions such as location of each CMG and the inertias for each CMG. And it will calculate the rotation matrices as well as the angular velocity and the attitude for at that current phase. And it will send the rotation matrices, attitude, and angular velocity into the control block.
And then now moving into the control block, we have similar inputs that are coming from the dynamics block that are being propagated into the control law that we went over earlier. And the control law will output a moment, which will be inputted back in, which is one of the outputs that goes back into the dynamics block. And it's also inputted into our steering law, which takes more outputs from the same dynamics block, as well as some constants, and outputs the different gimbal rates and wheel accelerations that will then be propagated forward with time.
All right. So in real application, these CMGs could be used to stabilize the spacecraft due to vibration. And CMGs are often used for attitude control and stabilization of a spacecraft. In our class, we only really consider single axis and constant speed though. So this would be adding a couple more levels of complexity as we'd be changing the speed, and we would have we have one extra gimbal frame. So the control device will receive information on where the spacecraft is pointing, and then it'll send out information in order for the spacecraft to like point in the desired direction. The control technique proposed in the paper emulates this as control as a control law. Continually takes information from the attitude of the plate and sends out information to update the attitude of the plate. Now, in reality, there might be some disconnects as information would probably go from whatever's measuring the attitude to a computer, and the computer would go back to the ADCS, and ADCS would probably send information back to the computer or other components. The paper is theoretical. It explains how control member gyros are used to maintain pointing with disturbance due to vibration, but does not test the theory with actual CMGs attached to an object. The model presents 4 CMGs in a pyramid configuration and a gyroelastic flat plate using the first 6 modes for vibration. By 200 seconds, the body rates have converged to 0 radians per second, and the vector portions of the quaternion are almost to 0 as they oscillate around 0, around 1 e to the -7. Gimbal rates converge to 0 radians per second, and the rotor acceleration also converges to 0 radians per second.
The simulation ran in MATLAB and Simulink used the same control laws as the discussed research paper. Running the physical vibration simulations through FEA was outside of our scope, so there were some assumed constants being inputted to the simulation that could actually be varying with time in vibration dynamics. The graphs did not properly converge as expected from the analysis done by Gia and Sean. There are likely also some small errors in the simulation, but it's difficult to find a good comparison because the simulation did not account for the variable vibration dynamics. Overall, getting the simulation to run was a success because we were able to work around from some singularities and we were able to simulate the controller on a very simplified system. Thanks for
Your
watching our presentation.